Also, we did one calculus, means one example for that, that how to find out the flow between two stream functions. Actually, and that would be, we have also found some, means translated that in some practical example, just like a distributions of the flow something. So in that case, if you know that somehow your velocity on the top, and obviously when you will go to the river bed or let's say any fixed surface, your velocity would be zero. And just because you don't know what type of velocity profile is, maybe parabolic or maybe straight line. Straight line generally doesn't happen actually. So most of the time parabolic or type of thing, half parabola, very full parabola. So without knowing that much complications, most of the time people take the linear variation. Actually, that is the easy to means approximate or calculate, because you know the velocity on top, you know the velocity on the bottom is zero, and you know the depth, so you can calculate slope. You can get equation of line in terms of velocity actually. So that is easy to calculate. So from there you can calculate the height where you will put a divider, so that you can divert the flow as per your need. So we did actually one example for that also. So in last class we were here that circulations, that what should be the rate of the circulations of the fluid within a particular amount actually. So in that particular part, what you have there, you want to how much fluid is moving in a that circular path. So practically circular path, we this is the definition actually. The line integral of the tangential velocity component about any closed fixed curve is called a circulation actually. And which is you are just velocity, you are multiplying by ds dot product, and that's called the circulation part. Let's see how can it be used actually. So, so if you have, let's say, this is your fluid or element here. At point O, you have considered, let's say, your x component of velocity is u, y component of velocity is actually 1 minute. So y component of velocity is v actually. So now what is happening here? So while doing your Taylor series expansion, so if you are moving delta x distance to x side, so you can calculate what should be the actually the velocity. So because if you are talking about x side velocity, so you can calculate what should be the velocity, because if you have in this side motion, so you can calculate that, and let's say you want to calculate what should be the velocity component v in this particular side here. So you have moved here delta x distance away. So you are finding its derivative, how it is changing with respect to x, and multiplying by delta x by 2. Okay. So that is the velocity component is going at this particular side. Same way for v component here, this side. So you can find what would be the magnitude of u. Because can you understand why this u is changing with respect to y? Because u is moving in this side. So plane of u is y actually. So u velocity would change with respect to the your y coordinate. Same thing v velocity. V velocity would change with respect to x coordinate, because this side is your plane actually. Okay, so wherever you have some, let's say, surfaces or stresses, the velocity would change only on that particular side. So here you got the velocity of v here. What should be the magnitude of velocity v here? You will get v del v upon del x u and this particular thing, right? So now we want to have that your dot product of your velocity, as we wrote the circulation part, we wrote v dot ds, right? So you know the velocity component, just multiply your ds and integrate it. So first you are moving from point O to A, then you are moving from point A to C, then you are going from C to B, and now you are coming back to B to A. So that is one circulation path. Is this fine till here?
Yes, sir.
So the started from point O, you move to point A, then you move to point C, then B, then O. So you complete one circulation path. Now, if you move from U to A, O to A, so your velocity is U multiplied by, you are doing line integration here. So you are doing U into delta x also because you have, well, B dot ds only. So ds is your distance. Okay,
Yes, sir.
fine. So you got U into delta x. So that's for this side. Now for from point this A to C, so you have, this is the velocity in y direction, multiply from your delta y. So that you reach at point number, this point number C here. So you have this v plus del b upon del x into dx, multiply by delta y. So you reach to point C. Now from here to here, this side velocity component is this u plus del u upon del y into delta y. So this is this side. So you want to go this side. So that should would be the minus sign there. So you got here this side. Here you got minus u plus del u upon del y, delta y into delta x. Now you reach to point B. Now you are going back. So this side velocity was B. So you are going this side. So therefore you have put here the minus sign here, the v into delta y. So you reach to point O. So you completed one circular path completely. So if you will simplify it, you can also do in your the notebook means actually. So if you will simplify it, you are just getting this del v upon del x minus del u upon del y into delta x delta y. And this term, as we already talked about angular velocity, so this is actually angular velocity in x by plane, and its magnitude will go into z direction actually. So you will got two times of the omega actually. Now delta x delta y, because this dimension by delta x, this dimension by delta y, that is your area. So area, it would become now dA. So finally you got the expression of the circulation is that means integral close line integral v dot ds equal to, you got from this is a derivation 2 wz into dA, and w is angular velocity. So you can just write it in terms of cross product del into del cross b. So del cross b practically is vorticity. So vorticity is two times of angular velocity. So here it was omega. You have already have two here factors. So this become now vorticity del cross b into dA. So if you want to find the circulation per unit area, so your area will come in the denominator is equal to coming your just del cross b. Okay. So del cross b, which is your vorticity or two times of means angular velocity. So it is fine that how to calculate it.
Yes, sir.
Okay. So that way you can calculate that how much actually fluid will move in that particular area along that particular path actually per unit area. So this is the things to the actually the remember to you that vorticity per unit area means the circulation per unit area is equal to your vorticity is also equal to your two times of angular velocity, right? So that is the things to be remembered. Now you have these are some you can say examples where people used to have all this part. So one is this you have the simple thing people used to go merry-go-round thing. So here you move the rotate in same angular velocity as it right itself. So this is the some example of the rotational flow. You are moving on this particular path here. Then you have a merry-go-round again. So this is again a motion of rotational flow actually. Okay. Now why they will say here, then you will say the A is rotational flow, circular in the analogous to the roundabout, while B is irrotational flow. Why B is irrotational flow? Can anyone think about it? Huh? Yeah, I can hear actually. My video is automatically getting paused. I don't know what is happening.
So in
Yeah.
B part, the man is not rotating.
Uh,
The,
uh,
uh,
y-
uh,
okay. Yeah, in B part, the position of man
is
is as a okay.
and in A part, the position of that the child is also changing with the sun. So that is why it is considered as the rotational flow.
Right. Now, next part here that how to find this irrotational flow. So previously we have talked about the rotational flow. We calculate angular velocity, vorticity, then the circulation part. So this is also one type of flow. We always have it just like that. The sprinkling of water is the best example for that. Or sometimes we do the mixing of the fluid also in some tank or containers. So those are called some rotational flow type of the example. Sometimes we don't want. We just want a transportation only. So transportation, we just want a actually a long distance transportation. We don't want the rotational flow. We want practically a rotational flow. The flow should move in a particular side because so that we can travel a long distance. So most of the fluid transportations is actually irrotational. All pipelines, process industries, everywhere is irrotational flow only. Rotational is where we practically want to mix the something actually. Okay, mix the something, or we want to cover a particular area, just like in your gardening area, you want to cover some area without doing the movement by hand. So you are just putting a means a sprinkler there, and which cover the entire area over the period of time. So for irrotational flow, there the one term is called velocity potential. So as we defined previous one means the stream function, now we are defining something for irrotational flow is velocity potential. Now velocity potential is given by the symbol is phi, and for that velocity vector is given by this, that minus of del phi actually, and various velocity component are given by this way. Actually u is given minus del phi upon del x, v is given minus del phi upon del y, z is also given here, so minus del phi upon del z actually. Okay, so this is what here they have said here. The negative sign signifies the flow is always in the decreasing direction of velocity potential. So that makes sense actually. Here one way you have potential high, other way you have potential low. So your movement would go always from high to low, just like in your the electricity flow. So electricity move from high voltage to the low voltage side actually. So in that way, because you should have some gradient to move it. Okay. Or same thing in case of fluid flow also. So fluid will move from high pressure to the low pressure zone. So in case of transportation of the fluid, the pressure is considered as a potential actually. Don't confuse with that is with the velocity potential. Okay. Same thing, fluid will go always from high velocity zone to the low velocity zone because everyone wants to have a equilibrium, the state, or to minimize its energy. So you have to move from low to high, from high energy zone to the low energy zone. Fine. So now what you have here, so same thing you can write in the cylindrical coordinate. The cylindrical coordinate, your velocity component are given minus del phi upon del r, and b theta is given minus 1 upon r del phi upon del theta. So generally in UG curriculum, B that means the stick for two-dimensional part. So therefore these are here for two-dimensional only. Now you can write for third component also. So as I told that the W is minus del phi upon the del Z and Vz is minus del phi upon the del Z. Previously also we have defined one more thing, stream function. So stream function case, your velocity U is given del psi upon del Y, V is given minus del psi upon del X. Because the stream function satisfy your continuity. That's what we have proved also previously. And that velocity vector from the in terms of the stream function is given by this 1 upon r del psi upon del theta. V theta is minus del psi upon del r. Let's see what can we do from here. So let's say irrotational flow here. So we want to say here the irrotational flow or the potential flow automatically satisfy here this. So what we have proved for the rotational flow, what we have calculated, your angular velocity. Yes or no? Correct or not?
Yes, sir. Yes, sir.
For
Correct,
the
sir.
rotational flow, we calculated angular velocity. In angular velocity, we have calculated del cross V. So if del cross V is not equal to 0, it means it is the rotational flow. Now, if we want to make it the irrotational flow, so your del cross V must be equal to 0. Now we are the replacing by del phi. So at the place of V, we have just the substituted here del phi term. Covered for time being the sign convention. So plus minus sign here because we have taken V is minus of del phi here, right? Here this one. The V is minus of del phi. So we are not talking about the sign. So from here we can write your del cross V. We can rewrite here again the del cross del phi, and that must be equal to 0 for each potential lines, and to make the flow irrotational. Okay.
Yes, sir.
Now let's see what is 2D incompressible irrotational flow. From where will it come? I wrote here two equation here. What is first one? This one, del V upon del X minus del U upon del Y. What is this first one? Can anyone recall what is first one? This del V upon del X minus del U upon del Y. What is this?
Angular
It is
velocity.
angular velocity. That is angular velocity in XY plane,
Yes.
right? And we are talking about irrotational flow, right? So this must be equal to 0. So therefore, we have forced it equal to 0, right?
Yes, sir.
Now we know the expression of your V, we know your expression of U in terms of psi also, and in terms of phi also. Psi is the stream function and phi is your velocity potential. So we can check which one satisfy each of them. So if you would put your psi expression, your V is minus of del psi upon del X. That's what we wrote here,
Yes, sir.
this one. Your V is minus del psi upon del X. U is del psi upon del Y in terms of psi. In terms
Yes.
of phi, minus del phi upon the del X is U. V is minus del phi upon del y. So we want to say that whether the stream functions satisfy the angular velocity condition or not. So let's see for this part only. So this is what you have for your angular velocity. The first one, del v upon del x minus del u upon del y. For irrotational flow, this must be equal to 0. Now we are putting from the stream function, your v is minus of del psi upon del x. So we will put that here. So you will get a minus sign here, right? Minus of del square psi upon del x square. Now this side u is del psi upon del y,
Del Y.
right? So you will get, you already have here the minus sign. So finally you are getting here also minus del square psi upon del y square. So both the places you have the minus sign. So minus you can take the common. So finally you got del square psi equal to 0. It means you have the stream function also satisfy your irrotational means condition. Okay.
Yes.
Now let's see for continuity part. Now continuity, you have now velocity potential, velocity in terms of continuity, actually u in terms of velocity potential. So you have wrote minus of del phi upon del x. V you wrote del phi upon del y. Substitute here. So you are getting here del square phi upon del s square. Here also you are getting minus sign. Here also you are getting the minus sign here, del square phi upon del y square. Finally that is also coming equal to 0 आएगा नहीं आएगा?
Yes, sir.
Because 0 is this side, so that side is your continuity actually. So by means to say your stream function should satisfy your rotational means the angular velocity conditions, so del square phi, and your velocity potential should satisfy your continuity. Okay.
Okay.
Now, this is what in general you have here. Velocity potential is only the consequences of irrotational flow, whereas the stream function is the consequences of conservation of mass. Hello.
Yes, sir.
Now, second part, velocity potential can be defined for 3D flow. However, stream function can be defined only for 2D flow. Third point, these are the point to be the remember about your velocity potential. Third point is for inviscid, incompressible, and irrotational flow field are governed by Laplace equation. What is the Laplace equation? This one only. Laplace equations are these only. ये जो आपके पास आया है del square psi equal to 0 and del square phi must be equal to 0. These two equations are called Laplace equations. So finally your irrotational flow must satisfy these one, and then you can say for that is called the potential flow. If your flow is the satisfying your Laplace equation, it means that is your potential flow. Now potential flow is applicable for steady and unsteady flow both. So there are no question mark for the means unsteady characteristics. So it will follow for all, because you are just following two things. One is the rotational component velocity, other one is for your actually continuity. So those can be valid. for any flow, whether it is steady flow, whether it is the unsteady flow. So these are the 4 points you have to remember about your velocity potential. Okay.
Yes, sir.
Now, can you go back and check it something? Have we wrote everything correct here? I'm asking you people. Everything correct? Let's say first one, does it
Correct, sir. On this
satisfy
slide.
completely? Just try it, no? You have this. Now you can write your equation here. You try it. Just first term what you have here. First term what you have? Del P upon del X minus of,
Del U
बोलिए
upon
बोलिए,
del
Del U upon del Y.
del
Del
U
U upon
upon
del Y.
del Y. So
Del
just
Y.
check तो कर लीजिए सेटिस्फाई करता भी है कि नहीं, ये चेक करना है हमें. You have the expression of everything. You have the, I mean, the expression of U and B in terms of velocity potential also. You have the expression of U and B in terms of stream function also. Let's do one by one. So let's say we want to satisfy it from stream function. So stream function के लिए हमारे पास क्या क्या है? Can you tell what should be the expressions of B in terms of stream function?
minus del psi upon del x.
Del
So
Phi.
you have here a term minus
Del psi upon del x.
1 minute. Yeah. So you have here del psi. आप लोग भी कर लीजिए fast, so you can do much more faster than me. So del psi upon del x. Fine.
Yes, sir.
Oh, okay. So what should be for u?
Del psi upon del y plus.
Del psi upon del y with a plus sign, right?
Yes, sir.
Let's see what is coming. कुछ आता है यहाँ से?
Yes, sir.
क्या आता है बोलो?
Minus del square psi upon del x square.
So you are getting minus del square psi upon del x square. And next one is also getting same thing with minus sign, right?
Yes, sir.
Del square sign upon del y square. Are they zero? Is it coming zero?
No, sir.
No, na? It's not coming zero. Correct or not?
Yes, sir.
Now let's see for in terms of velocity potential. Okay. So let's start this thing, same thing in terms of velocity potential. इसीलिए तो यू आर ब्लाइंडली वहां बैठ के बस वेलोसिटी पोटेंशियल में क्या है यहाँ पे 5. Yes or no? You have 5 and here you have y, right? Yes or no? Here also you have 5 and here you have x with minus sign. Correct? Now let me copy it here. Now here you are getting this plus sign, here you are getting minus sign, and here you are getting इसीलिए आप ध्यान नहीं दे रहे थे और मैं वहां पे कुछ भी बोले जा रहा था, आप यस यस कर रहे हो। इज इट जीरो?
Sir.
Yes, sir.
It is zero, right? This is not equal to zero. So this is not equal to zero. So you can put a not equal to sign here. So what is concluding from here? That, no, actually, so sorry, this is phi, right? So what are you concluding from these two derivation? That stream function does not satisfy. बोलो बोलो आगे बोलो. Complete my sentence.
Potential.
Stream function does not satisfy irrotational uh, condition. Yes or no? This is the irrotational condition that del b upon del x minus del u upon del y must be equal to zero. Yes or no? For an irrotational flow. So if you are just putting your things from
Yes.
your stream function, your stream function is not satisfying that condition. It means you will have a streamline flow in a circular path also. That you already know. Yes or no? Stream function or a streamline can be present in the circular path also. It can present in a straight line flow also. Correct or not? Hello?
Yes.
So the stream function is not the criteria just to check your irrotational flow condition, because it doesn't satisfy that criteria. Now let's say velocity potential. If you are putting velocity potential, it is giving equal to zero. It means your velocity potential satisfy your irrotational flow conditions. However, stream function now take continuity now. So this is for irrotational flow condition, right? This is for irrotational flow condition. So that's the means practically your angular velocity. Uh, angular velocity, or you can say irrotational thing. Irrotational condition, right? Irrotational condition के लिए your angular velocity must be zero. Let's say next part. What about continuity? Continuity, can you tell what continuity is?
Del u upon del x plus del v upon del
Yeah,
y equals
so you can write from here that del u upon del x and plus here del v upon del y is continuity in your actually in your 2D plane, xy plane. Yes, right? 2D incompressible fluid, right? So this is your continuity. Sorry, this is your continuity for two. Part happening. This is your continuity for 2D incompressible flow, not steady or unsteady. That is not a condition here. Now let's see what you think the satisfy here. Does the stream function satisfy continuity or not? You already know it.
satisfy.
satisfy कर रहा है sir.
It's, it's satisfied. We have already proved it, right? So
Yes sir.
we can rewrite it once more if you want to write it here. So you can write here. So that is your place of this here. So this is your U. So this is your U here, and this is your V actually. With this you can write here. So this is your V. Now from here you will get the term in this particular way here, and here this should change by psi. So it is coming equal to your 0. So your stream function satisfy your continuity. Let's say velocity potential. What will happen for that?
Not
Yeah,
Not
satisfied.
satisfied.
not satisfied. So these are the conclusion from your things. You have here, this is your V. So V is at this place, and this is your U actually. So here, what is coming here? So del square, practically you are getting this one. So with the place here minus sign, here this is your phi actually, which is not equal to 0. So these are the things you have proved from here, that your velocity potential satisfy your rotational flow condition, stream function satisfy your continuity. Okay,
Yes, sir.
okay. And these equations, now let's say for this one, we have heard one more term, Laplace equations, right? So let's say what Laplace equations are. So I can tell you. So Laplace equations, from here you wrote the first one. There you got del square psi upon del square psi is called the Laplace equation. Same way the del square phi is also called the Laplace equation. Means you are taking a double derivative of that. Okay.
Yes, sir.
So therefore you wrote actually all of them here. So del square psi upon del square psi means you are calculating is double derivative with respect to x, then with respect to y, with respect to z. Okay, and that must be equal to 0. Those called Laplace equation. How would it come? Those are coming in case of the stream function. Those are coming from continuity. In case of velocity potential, those are coming from irrotational flow condition. Okay.
Yes, sir.
Okay, both are the Laplace equation where you will write a term del square psi. So that is for Laplace equation for a for a stream function. Same thing you can write for velocity potential. That will come from your irrotational flow conditions. Okay. Now the next part here. Here one more thing is equipotential line. So equipotential line says that if you have a line, or let's say you have an electrical line, you say this line having a voltage of 240 volt. So what does it mean 240 volt? That either you make a connection in the Jalandhar or you make in the Amritsar, everywhere you should get a 240 volt. Yes or no? So same thing is there in case of fluid flow also. Also equipotential means that its value should not change along that particular line. So that's the way you are saying that lines of constant potential functions is called equipotential lines, and here that phi is constant, so you say the total d phi should be equal to 0, and then you are finding d phi here, del phi upon the del x into dx, del phi upon del y into del y, because this means velocity potential is 3D function. You can also write one more term here, del phi upon del z into dz. But if you are writing it for 2D flow, so you are just considering first two term only for 2D flow. Now you can substitute your actually things. This is del phi upon the del x you have taken in terms of u is minus u. Del phi upon del y is being considered as minus v, right? Yes or no?
Yes, sir.
Now from here, if you will the means the arrange it, you are getting del y upon del x is equal to minus u upon v. So this is the equipotential line. Now similar to do this, you have for the streamline. Streamline is dy upon dx equal to v upon u. So just you have the actually you have reverse with minus sign. So practically these are the two lines which are perpendicular to each other because their cross product is minus 1. So have you seen in your 12th standard that when you want to check whether two lines are the perpendiculars or not, you are multiplying by their slope, and if their product is coming minus 1, then they are perpendicular. Yes or no?
Yes, sir.
So
Yes,
same
sir.
thing we have proved here also. So first thing we have derived the equation for equipotential line. So from this first four line, we got it minus u upon v. Streamline, we already know that del y, dy upon dx is v upon u. We did a cross product of that. And finally, that cross product is coming minus 1. It means these two lines are always perpendicular to each other. So this is the derivation just to show that whether equipotential lines are perpendicular to the stream lines or not. So I hope you can do it. You can remember also. Fine.
Yes, sir.
Now this is a graph for that, the equipotential line and stream function. The stream function you have defined for the stream lines, and equipotential lines you have defined in this way. Actually, so this as from previous one, you have just did that they are perpendicular to each other. No matter they can have the straight line also, they can look at a curve also. Here you can say the curve. Only thing that point they are intersecting, they are perpendicular at that particular point. No matter what is happening in between of that. Because from here to here, you don't know. But practically, if you want to draw all streamlines, all stream functions, so you will have seven streamlines in between of that. So if you are changing that, every point where they are intersecting is actually a 90-degree angle. Okay?
Yes, sir.
Hello? Now let's see what this is being mentioned for flow net. So previous वाला जो part है ये flow net. How would this flow net would be the useful? Can you think that something? So you can think maybe from these lines. First thing is that velocity at various points in a flow are inversely proportional to spacing between the streamlines and equipotential lines. What does it mean actually? Can you recall something from here? Just give me 2 minutes only, just to explain this slide. Velocities at various points in flow are inversely proportional to the spacing between the streamlines and equipotential lines. What does it mean actually? Well, let's see from this previous graph. You have the streamline here. These are, let's say this is coming from these two lines. Here they are close, right? Yes or no?
Yes, sir.
Now here what happened? They are very far away here.
Yes, sir.
Why does it happen, and can I correlate this at this particular point here? Velocities at various points in the flow are inversely proportional to the spacing between the streamlines and equipotential lines. Anything?
सर जहाँ पे स्पेसिंग कम है वहाँ पे वेलोसिटी ज्यादा है।
Yes, जहाँ पे spacing कम है, where velocity is more, because you have previously proved that the stream for a the stream function, the difference between two is just a flow rate. Yes or no? You have proved already that. Now flow rate is same. Flow rate is same. So what will happen that wherever you have, they are very far away. What will happen then? So to make the same flow, to compensate for the flow rate, where the area is more, so what do you have to do? You have to decrease the velocity. Hello?
सर
Are you getting the point? Where, because your flow rate is same between two streamlines. Now the question is that wherever streamlines are far away, you are decreasing the velocity to compensate it, because finally it is the product. Velocity into area is just a flow rate. No response from anyone? Can anyone hear me, or nobody can hear?
यस सर
So this is the point with the, okay, you have class. So we have here, so wherever the streamlines are far away, it means you have to decrease the velocity in order to compensate your flow rate. Wherever they are close, means velocity is high. Okay. Now, next part is there. Network is useful to estimate the velocity at a different point in a flow field when it is not convenient to use analytical solution. So, whatever net you have made previously, this net, this net, it would be helpful just to calculate the velocity between different points, because analytically you cannot find the velocity at each and every point of the flow, and for that you have to do a lot of tedious calculations. So this particular thing would help you just to calculate your actually velocity at different points. How would it calculate? Let's say somehow you have calculated velocity at this point. This you already have it. Okay. Now you have the means expressions for phi. Phi is given minus del that u is given minus del phi upon del x. So somehow you know that velocity at this particular point. If you want to calculate another point, you are just differentiating it, extending it only. So you can easily calculate the velocity at all these points here, point here, point 2, point 3, point 4. Okay, that is the importance of this flow net. Without doing any further tedious calculations, you can easily calculate velocity at different junctions. So we will do one example of that, then you can understand in the actually the next class. So we will end here today. Okay.
ओके सर
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
सर